So, good evening and welcome to the inaugural Madingley Lecture. The Madingley Lectures are the Institute of Continuing Education's new public lecture series here at Madingley Hall. I'm the Director of Continuing Education, and the first thing I would like to do this evening is to take the opportunity to introduce the Vice-Chancellor, Professor Sir Leszek Borysiewicz, so that I can then allow him to introduce our speaker tonight, Lord Rees, and then to chair questions at the end of the lecture. So, the Vice-Chancellor, the university's 345th Vice-Chancellor, was installed very recently on the 1st of October 2010. So I'm particularly grateful that you're able to join us this evening so early in your term. Sir Leszek was previously Chief Executive of the UK's Medical Research Council, and prior to that, from 2001 to 2007, was at Imperial College London as Principal of the Faculty of Medicine and later as Deputy Rector, where he led the development of interdisciplinary research between engineering, physical sciences, and biomedicine. In a sense, however, this is a return to home, as Sir Leszek started in 1988 as a lecturer in medicine here at Cambridge, from where he went on to be Professor of Medicine at the University of Wales in Cardiff, where he led research which carried out pioneering work on vaccines, for which he was knighted in 2001, and in particular led clinical trials in therapeutic vaccine development for HPV, human papillomavirus, which is one cause of cervical cancer. Sir Leszek was the founding fellow of the Academy of Medical Sciences in 1996 and member of its council from 1997 to 2002. And he became a fellow of the Royal Society in 2008. So I would like to welcome Sir Leszek and Lady Borysiewicz. And just before I hand over to the Vice-Chancellor, just to remind you that if you have your mobile phones, please could you switch them off at this point. So thank you.
Well, Rebecca, thank you very much indeed. Firstly, congratulations on the initiation of this lecture series, and actually of the Institute of Continuing Education. It's my first visit here, but it's wonderful to see the programs and the activities that you plan for the future with the team. So the very best of luck, and I do hope I will have the opportunity to attend many of the events that you have here. There's an old-fashioned cliche, which is the speaker needs no introduction. Unfortunately for me today, that is absolutely true, and I could sit down at this point. Lord Martin Rees is, or was until December, President of the Royal Society, and probably, I would say, one of the, if not the most eminent scientist in the United Kingdom. He was Astronomer Royal, as well as holding a series of titles, including the Master of Trinity College here in Cambridge. His interests in astronomy and in cosmology are well known to all of us. But perhaps for most of us, he has become, in many ways, the voice of British science. Through the last 2 to 3 years, it has been my privilege to work very closely with Martin, and he has been a consummate voice of good advice, warning against where it's appropriate, warning against the issues about reductions in support for science and the impact that this would actually have on this country, always doing so on the basis of where evidence will be able to support that particular call. And those of you who may doubt it, please get onto your iPlayer and listen to the Rees lectures, because you actually need to hear no more than how convincing Lord Martin Rees can be. And I'm sure today he'll be just as convincing in his chosen topic of life in the cosmos. Martin, over to you.
Thank you very much, Vice-Chancellor. ladies and gentlemen. Okay, yes. Right. If you were to take 10,000 people at random, 9,999 would have something in common. Their business lies on or near the surface of the Earth. And the oddball will be an astronomer. And I'm one of that small minority. In fact, if you were to do the survey not in a random place on Earth, but in King's Parade, you'd find a slightly higher proportion of astronomers, maybe 1 in 1,000 or 1 in 500, because Cambridge is, I'm glad to say, one of the places where astronomers are heavily concentrated. We're one of the world centres for astronomy, and I'm privileged to be part of this community. So, with that, let me emphasise that astronomy is not just for astronomers. I think it's important that the night sky is something which has fascinated people from the dawn of humanity. We've all had different environments to grow up in, but we all look at the same night sky and wondered about it, interpreted in different ways. So the night sky is part of our environment, and it's something that we have all wondered about. And also, it's part of our culture to understand astronomy and its nature. And we now know that our origins lie in the stars, and that our remote descendants may roam among them. And I'll ask in this lecture, what were the features of our universe that allowed stars and planets to form, and which led on this planet to the emergence of our biosphere, where, in the famous words of Darwin, the closing words of Origin of the Species, whilst this planet has been cycling on, according to the fixed law of gravity, from so simple a beginning, forms most wonderful have been and are being evolved. Well, astronomers tried to go back before Darwin's simple beginning to set the Earth and the atoms that it was made of in a broader context. And we also want to ask the question, could there be life elsewhere? But before that, I want to say a few words about whether human life is going to go into space. Are we going to go beyond the Earth ourselves? And people for centuries have speculated about that. And among them was the great Isaac Newton, probably the most eminent alumnus of this university. He speculated about life in space. He was, incidentally, a most unattractive personality, quite unlike Darwin. He was solitary and obsessive when young, vain and vindictive in his old age. So he wouldn't have been attractive, although on an IQ test he'd have beaten almost anyone else hands down. And he was the first, really, to think about how, in Darwin's phrase, planets go cycling on in orbit. This is a nice picture taken from the English translation of his great book, the Principia. You can see what's happening. A cannon is firing a projectile from a mountaintop, and if it's fired fast enough, then the trajectory curves downwards no faster than the Earth curves away underneath it. It goes into orbit. This, I think, is still the neatest way to explain to beginners the nature of orbital flight. It's quite easy to understand here. Now, Newton could have calculated that to go into orbit, the cannon has to fire the projectile at 18,000 miles an hour. Far, far beyond, of course, the capacity of the cannon of his time. And as most of you know, it wasn't until 1957 that the Sputnik went up into orbit. And after that, things moved very fast. It was only 12 years later that we got views like this from people orbiting the moon. And the moon landing was 12 years after Sputnik, only 66 years after the Wright brothers' first flight. And most of us probably then expected that by now there would have been a lunar base, maybe an expedition to Mars, but that hasn't happened. 2001 didn't resemble Arthur C. Clarke's vision any more than, fortunately, 1984 resembled Orwell's. That's because the political impetus for manned spaceflight was lost. after the Apollo venture. And only the middle-aged can remember seeing live on TV Neil Armstrong's first small steps. Young people today, indeed, know that the Americans landed on the moon, just as they know the Egyptians built the pyramids. But both enterprises may seem driven by equally arcane national goals. But it was a heroic episode, and I'm rather proud to have this picture signed by 7 of the Apollo astronauts. And since that time, hundreds of astronauts have not been to the moon, but they've circled the Earth, many in this space station. Activities that, compared to Apollo, seem perhaps neither very inspiring nor very practical. But despite this sort of languishing of manned spaceflight, unmanned probes to other planets have revealed varied and distinctive worlds. And let me show you first a few pictures of Mars. This is a picture of the surface of Mars, and here are some taken from the European Space Agency's Mars Express. This is a big crater, and the next picture is going to show a close-up of the side of the crater there. A slightly terrestrial-looking landscape, but you can see that Mars has very interesting terrain indeed. And this is the Phoenix spacecraft, which landed on Mars a couple of years ago. This is going to dig down to a depth of about 1 meter to analyze the sample. Not to bring it back to Earth, of course, but to analyze it in situ. And, of course, space probes have been further. Here's Jupiter, its moons, first discovered by Galileo, of course. This is Europa, which is a close-up of Europa. It's got almost certainly oceans under this deep ice. Here's Saturn, a spacecraft called Cassini. Went to Saturn a few years ago, and it's still orbiting around, taking close-ups of all the moons. And one of the most remarkable outcomes of this was the exploit of a European robotic probe called Huygens, which was released from Cassini. And what it was supposed to do was to land on Titan, which is the giant moon of Saturn, the biggest moon in the solar system. It was supposed to open a parachute and land on a surface about which we knew very little. And it did just that. Here, the left and in the middle are pictures taken on the way down. There on the right is where it landed. Now, this looks rather like terrestrial topography, rivers, and even a little lake. But there's a difference. These rivers are liquid methane. The temperature is minus 170 degrees centigrade. And those little rocks are solid methane, probably. So no sort of beachfront property there. It's not a very comfortable place. But this is a remarkable achievement because this robot, it wasn't being controlled from Earth because a radio signal takes hours to get to Saturn and back. So for the last 2 weeks, when it was released from Cassini, this craft was on its own. This is a great triumph of technology that it did this. Well, I hope that during the next few decades, the entire solar system will be explored and mapped by flotillas of tiny robotic craft, doing things like this on all the objects in the solar system. But are people going to follow them? This shows Harrison Smith, the last man on the moon. The practical case for sending people into space is getting weaker all the time with each advance in robotics and miniaturization. Indeed, as a scientist or practical man, I see no case for sending people into space at all. But as a human being, I am quite an enthusiast for manned space missions, in that I hope some people now living will walk on Mars. It should be a long-range adventure for at least a few humans. But this goal is actually receding. NASA's firm plans don't even include a return to the moon. I think that's really because NASA projects are always very expensive because they have to be achieve very high safety standards to commit civilians to something like that. But I think, therefore, that future expeditions to the moon and beyond will only be politically and financially feasible if they are cut-price ventures, perhaps privately funded, accepting higher risks, and perhaps spearheaded by individuals who will accept these risks, and even one-way tickets. There will be people who will do that. And perhaps it'll be private sponsorship, and I could talk a bit more about this afterwards. It's not crazy, I think, to do it that way. But it will be dangerous, and remember that nowhere in our solar system offers an environment even as clement as the Antarctic or the top of Everest. So it's kidding yourself to think that going into space is an escape from the Earth's problems. We've got to solve the Earth's problems here on Earth, not in space. But there could nonetheless, if we think a few centuries ahead, be self-sufficient groups of pioneers living away from the Earth. They would surely then use all the resources of genetic technology to modify themselves and their descendants to adapt to an alien environment of much lower gravity. The post-human era would then have begun, and machines of human intelligence could then spread still further. And whether the future lies in the long run with organic post-humans or with robots is a matter for debate. Well, our Earth is very tiny, but it could therefore be the seed from which life could spread through the galaxy in the very long run. But let's now widen our gaze beyond our solar system, far beyond the reach of any probe we can now conceive. It would take tens of thousands of years for any probe to actually get to even the nearest star. So could there be life out there already among the stars? What about the stars themselves? We've learned enough about stars to understand them, their life cycle. We see places where stars are forming. Here in the Eagle Nebula, about 7,000 light years away, there's enough dusty gas to form hundreds of new stars like our Sun and solar systems. And we see stars dying. This is what our Sun will look like in 6 billion years. Here's another star dying in a rather messy way, as it were, here. And some stars, particularly big stars, die rather explosively. This is a famous object called the Crab Nebula, which is the exploding debris from a supernova explosion witnessed by Chinese astronomers in the year 1054 AD. The star flared up then, and we now see this exploding debris. You might think that these dying stars far away are irrelevant to us, but were it not for these exploding stars, we wouldn't be here. The reason for that is that stars derive their energy by nuclear fusion. They start with hydrogen and helium, and they gain energy by turning hydrogen to helium, then helium into carbon, into oxygen, into iron, and so on. And then, when they die, they throw it all back into interstellar space, and new stars form from it. And in fact, I'm not going to explain all this diagram, but there's a sort of ecology going on in interstellar space where new stars form, and then when they die, they throw back material into space, and that space is enriched with the heavy elements of the periodic table, which are made during the lifetime of the star, and then they make new stars. And we can understand enough about this to understand why oxygen and carbon are common, gold and uranium are rare, and how they came to be in our solar system. We know that every atom in our bodies was made in a star which died before our solar system formed. We know indeed that we have inside each of us atoms that came from thousands of different stars spread through the entire Milky Way. So we are literally the ashes of long-dead stars, or if you're less romantic, we are nuclear waste from the fuel that made stars shine. And I'd like to put in a plug for Fred Hoyle, who is in fact my predecessor as Plumy Professor of Astronomy here, and he was the person who, more than anyone else, explained and quantified this wonderful story, which shows that we are linked to the stars in an even more intimate way than the astrologers think. We are actually made of stardust. And all the atoms that we are made of do have this history, which we can trace back to far earlier times than when the Earth was formed. We've now, in just the last 10 years or so, learned something which makes the night sky much more interesting than it was to our forebears. We've learnt that most of the stars we see in the sky aren't just twinkling points of light. They're orbited by planets, just as our sun is orbited by the planets we are familiar with, including the Earth. Most of these planets aren't detected directly. They're detected in the fashion indicated here. If a star is orbited by a planet, then what actually happens is that both the star and the planet orbit around the center of mass of the system. It's called the barycenter. The planet moves in its orbit. The star, being heavier, moves in a much smaller orbit. And even if it's not possible to observe the planet, it has proved possible to observe the small motions of a star induced by an orbiting planet. And by this method, in the last 10 years, several hundred stars have been observed to have planets around them. And it's possible to infer the mass of the planet and to infer its orbital period. Don't worry about the details, but I just put up here on this slide, this is a list of stars which are inferred to have at least 2 planets discovered this way by sort of Fourier analysis of the motions of the star. And there's one star which is known to have at least 5 planets found in this way. Now, most of the planets found in this way are big planets. They're rather like Jupiter and Saturn, the giants of our solar system. It's not possible by this indirect technique to find a planet like the Earth, because that would induce a motion of only a few centimeters per second in the star it's orbiting, and that centimeter per second motion is too small to detect by the methods used. But there is another way, which is going to, within the next year or two, tell us how many Earth-like planets there are orbiting other stars. And this is being done mainly by a spacecraft called Kepler, which was launched in March last year. What Kepler is doing is it's looking at the same part of the sky continuously. It's looking at a region 7 degrees across, and it's measuring the brightness of 100,000 stars in that part of the sky with a precision of better than 1 part in 10,000, and doing that every half hour. And what it's looking for is a transit by a planet, because supposing that there's a star and there's a planet and the plane of the orbit is along our line of sight, and if the planet moves across in front, it blocks out a bit of the starlight, and the brightness of the star will dip a bit, as shown there. And if you have an Earth-like planet orbiting a Sun-like star, then just the ratio of the areas, it's about 1 in 10,000, so the dip is just 1 part in 10,000. But the Kepler mission ought to be able to detect that, and in order to be sure you've seen a planet, then you've got to see 3 of these dips occurring regularly, and if it's like the Earth going around the Sun, that's going to take 3 years, and so we have to wait a year or two before we get some data from Kepler on Earth-like planets. But it'll come, and that'll give us an indication for how many planets there are that are closer to the size of the Earth than to the size of Jupiter. Now, this is still a bit unsatisfying, because we're seeing the shadow of the planets, not the planets themselves. But to detect an Earth-like planet orbiting another star is a much more challenging task. It's very challenging because let's imagine you were looking at our solar system from 50 light years away. This is a nearby star. Supposing some alien astronomers are out there looking at us. then from a distance of 50 light years, our sun would look a very ordinary star, and the Earth would look, in Carl Sagan's nice phrase, like a pale blue dot, about 10 billion times fainter than the sun, and separated from it by a tiny angle, fraction of an arc second. So the task is really like looking for a firefly next to a searchlight. It's a real challenge. You need sensitivity and resolution. And we have to wait some time until we have arrays like this in space, or the next generation of telescopes like this on the ground. Look at the scale of the lorry there. But one of these is being talked about to be built in the next 15 years. And they will be able to detect pale blue dots orbiting other stars that might be like the Earth. Now, once one of these can be detected, then you can learn a surprising amount about it. Because, again, suppose the alien astronomers were looking at our sun and our Earth. Then they would find that the shade of blue would be slightly different depending on whether the Pacific Ocean or the landmass of Eurasia was facing them. So alien astronomers from 50 light years away could infer that the Earth had continents and oceans, the length of the day, something of the climate and seasons, and perhaps by studying the reflected light that there was oxygen or ozone in the atmosphere. And that's the kind of thing we'd be doing in about 20 years when we can detect Earth-like planets around other stars. And once we can find one, we can find zillions of them. So this would be a very exciting development. Well, the next question, of course, is, do we expect life on any of these? And this is a much more difficult question because we know too little about how life began here on Earth to be able to say whether life is likely or unlikely. Of course, people are looking for evidence for life in our solar system, in all these sorts of places. No one's very optimistic. The best you might find on Mars is sort of freeze-dried bacteria that lived a few billion years ago and now dead, and we don't hold out much hope elsewhere. But on these other planets around other stars, then, of course, there may very well be life. There may very well be a biosphere. And it's obviously sensible to focus on Earth-like planets orbiting stars like the Sun. Some people, of course, have argued that our Earth is very special indeed. I won't go into this, but they said that our Earth's special. It's got a moon that's special, and that Jupiter has to be there, etc. But I think we mustn't be too impressed by this sort of argument. I mean, we've evolved in symbiosis with our environment, and we wouldn't be the way we are unless the Earth had its properties. But that doesn't mean that there couldn't have been life in a rather different environment. We've clearly evolved to fit our environment, but it's rather like saying, isn't it amazing that your legs are just long enough to reach the ground? It's not really amazing at all, and it may not be amazing that we fit our environment, and therefore I think one should be open-minded, and one should look for evidence of life on all other kinds of planets. And of course, science fiction writers have given us all kinds of other ideas, floating creatures in the atmospheres of planets like Jupiter, or even creatures not on planets at all. And incidentally, I tell my students that it's a good stimulus to your imagination to read science fiction, and first-rate science fiction is probably better than second-rate science in that it's more entertaining and perhaps no more likely to be wide of the mark. Of course, even if simple life is common, then it's a separate question whether it develops into what we call advanced life, still less intelligent life. We don't know. Because there's a lot of debate, as you probably know, about whether if evolution will rerun on the Earth, where you end up with human beings or not. You might end up with a planet covered with insects or something like that. We just don't know what's contingent and what is inevitable about evolution here on the Earth. And so I think we have to be entirely open-minded and realize that we don't understand the origin of life on Earth. Of course, there are people who think they do know about this, and there have been UFOs here, and they've been visited and abducted. And I get letters from people like this in my role as Astronomer Royal. I mean, I do two things. I encourage them to write to each other. That's often a good move. And also, I would say to them more seriously, do they really think that if the aliens had made the effort to come to the Earth and had the technology to do this, would they just have despoiled a few cornfields and made corn circles, met one or two well-known cranks and gone away again? It doesn't seem very likely. So I'm pretty convinced that we haven't yet been visited by aliens, but nonetheless, it's not crazy to believe that they may exist out there, and I think it's a good idea to use all possible methods to search for them. Well, of course, there are, as you probably know, some efforts being made to look for some sort of signals of the kind that might emanate from a planet where there is intelligent life. I don't hold my breath for success. I'm glad people are doing this because, of course, to detect any manifestly artificial signal, even if it was as boring as the digits of pi or a set of prime numbers or something, would carry the momentous message that maths and logic, if not consciousness, was not limited to the hardware in human skulls, but it evolved somewhere else. So that would be crucially important. Would we have any common culture with these aliens? Well, actually we would, because even if they live on planet Zog and have 7 tentacles, they would be made of the same atoms as us. They'd gaze out, if they had eyes, on the same cosmos, and the physics would be the same. So we would have something in common, and maybe we could understand their messages. But of course, we would have plenty of time to think about sending a message back, because remember that the nearest such life would be many light years away, and so it would take decades to send a signal, so there's no scope for snappy repartee, as it were. But, of course, there may not be anything out there. Perhaps all these searches will fail. It could be that Earth's intricate biosphere is unique, even if simple life is common elsewhere. And that may be disappointing to some people, but it would have its upside, because our tiny planet would then, small though it is, be perhaps the most important place in the galaxy, perhaps even a seed from which life could spread through the entire galaxy. But it's no saying that absence of evidence isn't evidence of absence, and there could, even if we don't detect anything, be intelligences that are leading contemplative lives out there, or so different from us that we couldn't recognize them at all. Well, that's a difficult subject because biology is very hard. I'm going to go back to the simplicities of the physical world, but extend our gaze still further from our own Milky Way galaxy to other galaxies. If we were to get 2 million light years away from the sun and look back at our galaxy, we'd see something like this. This is, in fact, I'm sure most of you know, the Andromeda galaxy, our nearest neighbor in space, 2 million light years away, and it's a spinning disk viewed obliquely, almost edge-on, where all the stars are orbiting around some central hub. And these galaxies are the basic building blocks of the large-scale universe. Here's another one. This is a disk viewed almost face-on. You might ask, how can we astronomers understand the nature of these, what they're made of, what their dynamics is, etc.? We can't do experiments on them, of course, in the way that particle physicists can crash particles together in an accelerator. But we can do experiments in the virtual world of our computer. We can ask what would happen if you crash 2 galaxies together. And here's a simple picture of what happens. 2 galaxies are falling together. The gravitational pull of every star in one is actually on every other. And you end up with a sort of mess like this. So that's a calculation. We then look in this sky, and as well as the galaxies I showed you, we see galaxies like that. And it's a pretty fair assumption that what happened here is rather like what happened in that movie. 2 galaxies have got dangerously close. The gravity of each one has pulled out a tidal stream on the others. And perhaps these, if we came back in 100 million years, would have merged completely. Because remember, that last movie was speeded up by about 10 to the 15 from real time. So it's by doing these calculations with different assumptions about the mass and etc. that we can come to understand in quite a lot of detail galaxies. And of course, we have huge numbers of galaxies to study. This is a map, as it were, of all the galaxies within a few 100 million light years of us. They're grouped together in clusters. Now, the one thing we know about galaxies is that they're moving away from us. This is a famous expansion of the universe discovered by Edwin Hubble in the 1930s. And there's Edwin Hubble, a heavy smoker there, as you can see. And he was the person who first realized that the galaxies were moving apart from each other. What he found was what's symbolized here, that the further away a galaxy is, the faster it's moving from us, symbolized by the longer arrows further away. Now, at first sight, when people are told this, they think this must mean that we are in some central position. But it doesn't mean that, as I can illustrate by this picture. Imagine this infinite lattice, and imagine that all the rods lengthen at a certain rate. Then if you sit on one of the vertices, then the other vertices will recede from you at a speed proportional to the number of intervening links. So the whole network will seem to expand. And that's quite a good way to visualize the expanding universe. If you imagine the galaxies linked together by rods, and all the rods lengthen at the same time, then that's going to give you the law that Hubble discovered. There's just one thing which is not fully represented in this picture, and better by this second Escher diagram. This is Escher's angels and devils. And this extra effect stems from the fact that light takes a long time to get to us from these distant galaxies, many billions of years in some cases. And so if we look a long way away, we're looking back in time to when the rods were shorter, when the lattice was more compressed. And so what we actually see when we look out into space and back in time is better represented by this picture here, when as we look far away, we see things as they were younger, and when everything is more closely packed together. And we can, in fact, look very far back indeed. This picture is taken with a very large telescope, and it shows a small patch of sky. It would take 100 patches like this one to cover the full moon in the sky, just a very small one. And it would look completely blank, looked at with a small telescope. But here, with a really big telescope, you see these several hundred smudges. Each of those smudges is a galaxy, many of them fully the equal of our galaxy or Andromeda, looking so small and faint because of the huge distance. And we're looking back at these galaxies to a time when they'd only recently formed. And in fact, if we study light from them, we can see they're not like our galaxy in two respects. First, they've got more gas in them, which hasn't yet made it into stars. And secondly, if you take the spectrum, you can see how much carbon, oxygen, etc. there is in them. And there's less than there is in a present-day galaxy, because there hasn't been time for the stars to make all those heavy elements in this galaxy. And so if we look at Andromeda, then maybe there are astronomers on Andromeda looking back at us, but there are certainly no astronomers on these very distant galaxies, because there's been no time for the elements to be produced to make planets, which require lots of silicon, oxygen, and iron, etc., and so therefore the scant chance of life. But what about still earlier times, before the first galaxies formed? We are confident, and have been since the 1960s, that everything started off in what we colloquially call the Big Bang. Everything was hot and dense. The best evidence for this is symbolized in this picture here. Even intergalactic space is not completely cold. It's warmed to about 3 degrees above absolute zero by very weak microwaves. And these microwaves, if you observe different frequencies, they have what physicists know as a black body spectrum, which is what you would expect if this radiation was produced in conditions like the center of a star, where everything is very hot and dense. And as the universe expanded and cooled, this radiation shifted into the infrared and then into the microwave band, but it's still around, it fills the universe, it's got nowhere else to go. And this is a relic of the time when the universe was only a few seconds old. Well, when people are told that the universe started off as this sort of amorphous fireball, one question they ask is, well, how did it get from that state to the present universe where we have tremendous structures? We have stars and galaxies, etc. It may seem contrary to the famous second law of thermodynamics, which says that order gets washed out. But the reason that doesn't happen, it's the effect of gravity. What gravity does is that if there's a tiny density contrast, then as the universe expands, that a slightly overdense region lags behind more and more and eventually condenses out. And I'm going to show you another movie which shows a simulation of a region of the universe big enough to make several hundred galaxies. And the expansion is being subtracted out, so everything is looking at the same scale. If you look, the time is on the bottom there, and you see that structures are forming. The universe expands, density contrasts grow, and imperceptible initial fluctuations eventually condense out into what turn into galaxies today. So this is the way in which we think an almost amorphous early universe developed into galaxies. And we'd like, of course, to understand this in a lot of detail. I've run out of time to go through this, but we can ask, what did the universe have to be like to allow this transition from something that was initially featureless and dense to something which developed structures and then develops planets and then eventually life? And these are some of the prerequisites. I'll go through this fairly quickly. Well, there's got to be gravity to pull structures together, but it turns out that the weaker gravity is the better, because that allows very large structures to form. If gravity was much stronger, then objects as big as us would get crushed by gravity, which would not be good. So we want a very weak force of gravity. Obviously, things must be in thermodynamic equilibrium. We've got to end up with some places which are hot and some which are cold. We need to have matter-antimatter asymmetry, because if we had equal amounts of matter and antimatter, then as the fireball cooled down, they'd annihilate, we'd have just radiation, no atoms. So we need that. And we also need what I call non-trivial chemistry. We need fundamental laws such that the nuclear force and the electromagnetic force are in balance, because in a complex atom like an atom or a nucleus of oxygen, then it's a balance between the nuclear force holding it together, the electric forces tearing it all apart. So we need some sort of fine-tuning there. And, of course, we need stars to form, maybe second-generation stars, because the first-generation stars make the first chemical elements. And we also need the expansion to happen at a well-tuned rate, because if the universe was expanding too slowly, it would recollapse very quickly before there was time for anything to happen. If it was expanding so fast, then structures wouldn't be able to pull themselves together because of gravity. So we have to understand this sort of well-tuned expansion rate. And we also need to postulate some non-zero fluctuations in the very early universe, because if the universe started off completely smooth, then it would now, after 13 billion years, be just cold neutral hydrogen, no stars, no galaxies, and no people. So the challenge of cosmologists is to try and understand why the universe was set up this way. Now, the one thing we do suspect is that to answer that question, we have to go back not to the first second of the universe, but to the first tiny, tiny fraction of a second. And the problem there is that if you extrapolate back to the first tiny fraction of a second, everything gets hotter and hotter and denser, and conditions are reached where we lose our foothold in experiment. The densities and energies are such that we can't produce them in the lab. The energies are far higher even than you can produce in the LHC at Geneva. And so we are in speculative territory. But the answers to the questions of why the universe is the way it is will only be found when we can go back very early on. Some people would say very far back indeed, to the first trillionth of a trillionth of a second. And that's when the actual universe was that big. And what we call our present universe was just that size. And that's the era when we believe that many of the important processes were imprinted. And it's a challenge to think of some indirect way in which we can get an observational or empirical handle on this extreme physics. Well, I put up this hazard warning sign because I want to just spend the next few minutes on some slightly more speculative issues. One important question is, how extensive is the physical reality within the remit of science? Now, I've already said that we can see huge numbers of galaxies. We can see galaxies out to about 10 billion light years. But there's a limit to what we can see because light hasn't had time to reach us from beyond a certain distance, because the universe has a finite age. And just as if you're in the middle of the ocean, there's a horizon around you, but you don't think the ocean stops at your horizon. The same may be true of the universe. And most of us suspect that there is a lot more to our universe than the huge volume we can see. In fact, I think most of us would bet that it goes on thousands of times further. The reason for that is that if we look as far as we can in that direction and in that direction, the differences are only 1 part in 100,000. So if there's any sort of gradient towards an edge, then it's a very, very gentle gradient. But the universe could go on far, far further still, not to 10 to the power 100 light years, or even far, far more than that. It could even go on so far that all combinatorial options are fulfilled, and that there's another Earth where there's another set of people in a lecture room like this. That happens in principle if the universe goes on far enough. But this, of course, let me emphasize, is far, far, far beyond what we can ever directly observe. And even that's not all, because what I've talked about now is the aftermath of our Big Bang, as it were. But some people think that our Big Bang was not the only one, and could be other completely disjoint space-times. One idea is what goes under the name of brain worlds. The analogy here is, suppose you imagine a whole lot of ants crawling around on a sheet of paper. That's their two-dimensional universe. They might be unaware of another set of ants on a parallel sheet of paper. Now, one dimension up, we may be in a similar situation, in that there could be another universe just that far away from ours. But if that distance is measured in some fourth spatial dimension and we're imprisoned in R3, then we wouldn't know about it. And that's a possibility. Another idea is that it's almost like a vast version of Fred Hoyle's steady-state universe, where big bangs are happening in a very complicated way, symbolized in this sort of cartoon. So what we think of as our universe, with our horizon a lot beyond, is just one sort of bubble, and there are a whole lot of others. And this is an idea which is taken quite seriously, and it raises the other question about if there are many Big Bangs, then would they all be governed by the same laws? Because we know that the physical laws that prevail on Earth and in the lab are the same as in a distant galaxy. We know that if you take the spectrum of light of a galaxy, the hydrogen atoms, oxygen atoms are just the same. But of course, on a still vaster scale, that may not be the case. And it could be that our laws are sort of fine-tuned in a way that doesn't happen in some of the other universes. So this is, again, a speculation. If I wanted a logo for my research area, I'd pick this one, an Ouroboros. It depicts the interconnectedness of the microworld on the left and the cosmos on the right. And there are lots of links between the very small and the very large. Our everyday world of life and mountains is determined by atomic physics and chemistry. Stars, halfway up on the right, derive their energy from the nuclei within those atoms, halfway up on the left. And though I haven't had time to describe it, galaxies are held together by the gravity not just of what we see, but of dark matter, which is a set of particles, subnuclear particles made in the Big Bang. So there is a link there as well. The left-hand side, the microworld, is a domain of the quantum. The right-hand side is the domain of gravity and Einstein's theory. And to just think about 20th century physics, the two great highlights were Einstein's theory of gravity and the quantum theory. And these haven't yet been meshed together. That doesn't actually matter very much, because if you're a chemist, you don't worry about the gravitational force between two atoms in your molecule, because that's about 40 powers of 10 weaker than electric forces. On the other hand, if you're an astronomer trying to work out the orbits of planets or stars, then you don't worry about the fuzziness induced by quantum mechanics, because everything is so big that that's unimportant. But conceptually, one does want to mesh these together, and the context where we need that unification is the one symbolized, as it were, gastronomically at the top of the picture, when the entire universe is squeezed to the tiny size I mentioned, because then quantum fluctuation could, as it were, shake the entire universe, and we won't be able to fully understand those processes until we have a theory which unifies the quantum world with the space and time ideas of Einstein. And that is a challenge, unfinished business for physicists. But before leaving this diagram, I want to emphasize something else, which is that not only do we want to link the very large and the very small at the top, but as the third frontier, the very complicated. And that's emphasized by what's at the bottom, namely us. We are the most complicated things in the universe, and we are neither as small as atoms nor as large as stars. And we are complicated to an extent that we are the main challenge to science. In fact, I show here, this is a drawing by Isaac Newton's least favorite FRS, Robert Hooke. This is his first picture of a flea taken through a microscope. And I want to show this because even a flea is far more complicated than an atom or a star, because there's layer upon layer of intricate structure in something like this. And that is why most scientists work neither on the very small, on the left, nor on the very large, on the right, but on the very complex. That is the greatest of all challenges to science. And incidentally, we are, as human beings, midway between the atoms and the stars. It would take about as many human bodies to make up the sun as there are atoms in each of us. The geometric mean of the mass of a proton and the mass of the sun is 50 kilograms, within a factor of 2, I guess, of the mass of most people in this audience. So we are midway, and to understand ourselves, we have to understand the atoms we're made of, but we also have to understand the stars that made those atoms. Well, finally, I want to draw back from the cosmos, or from what may even be a vast array of cosmoses governed by different laws, and focus closer to the here and now. I'm often asked, is there a special perspective that astronomers can offer to science and philosophy? Well, first of all, obviously, we view our home planet in a vast cosmic context, and in the coming decades, we'll learn where there's life out there, so we can think about vast spatial extents. And incidentally, that doesn't make us any more serene. People say, does the fact that I think about these enormous arrays make me more serene about everyday matters? But I have to say, I worry just as much about tomorrow and next week as anyone else does. But more seriously, I think astronomers can offer a special perspective in a sense of an awareness of an immense future. The stupendous time spans of the historic past, the evolutionary past, are part of common culture, unless you're in Kansas or Alaska or some places like that, where perhaps they aren't, but apart from that, we're all aware that we're the outcome of 4 billion years of evolution on Earth. But I think even those of us who are familiar with this tend to feel that somehow we humans are the end of the process, we're the culmination of it. But that hardly seems credible to any astronomer. That's because, as this crude time lapse, which shows the formation of the sun and its eventual death, the sun is less than halfway through its life. It's been shining for 4.5 billion years. It will be another 6 billion before it runs out of fuel and flares up. And the expanding universe will continue perhaps forever. To quote Woody Allen, eternity is very long, especially towards the end. And any creature witnessing the sun's demise 6 billion years hence won't be human. They'll be as different from us as we are from a bug, because there's been more time for evolution between now and then than there has up till now. So post-human evolution here on Earth and far beyond could be as prolonged as the Darwinian evolution has led to us, and even more wonderful. And Darwin himself thought about this a bit. One quote from him. And incidentally, the future evolution may well be even faster than natural selection, where it takes 1 million years for a species to evolve. This evolution may take place on the technological timescale of genetics or of machines taking over. And levels of intelligence or insight may allow future beings to address questions we can't even pose. Just as quantum mechanics may flummox a chimpanzee, there may be some of these important questions which will not be understood by human brains at all. Well, back a bit closer to the Earth, we're all familiar with this picture of our planet from space. I showed it at the beginning, where the Earth's delicate biosphere contrasts with the sterile moonscape where the astronauts left their footprints. And we've had these images for about 40 years. But suppose some aliens had been watching our planet for its entire history, this 4.5 billion years. What would they have seen? Over nearly all that immense time, the Earth's appearance would have changed very gradually. The continents drifted, the ice cover waxed and waned, successive species emerged, evolved, and became extinct. But in just a tiny sliver of the Earth's history, the last 1/1,000,000th part, that's just a few thousand years, they would have seen the patterns of vegetation start to alter much faster than before. This signaled, of course, the start of agriculture and the appearance of human beings on the scene. And the pace of change would be seen to accelerate as human populations grew. And then these aliens watching us would have seen even more abrupt changes. Within 50 years, little more than 1/100th of 1/1,000,000th of the Earth's age, the carbon dioxide in the Earth's atmosphere began to rise enormously fast. The planet became an intense emitter of radio waves, the total output from all TV stations and radars, and something else unprecedented happened. Small projectiles launched from the Earth's surface escaped the biosphere completely. They went into orbit, they went to the moon, or to the planets and beyond. Well, if they understood astrophysics, the aliens could confidently have predicted that the biosphere would face doom in a few billion years when the sun flares up and dies. But could they have predicted this unprecedented runaway fever less than halfway through the Earth's life? So this indicates that even in the sort of concertinaed timeline, extending billions of years into the future as well as into the past, this century is a rather special one. It's the first in our planet's history where one species, ours, can really change Earth's entire future and could indeed jeopardize life's immense potential. And I think what happens in future will obviously depend on whether we do evolve sustainably, whether some of these projectiles launched from the Earth do establish independent communities away, or whether there is a sort of spasm followed by silence as perceived by these aliens. So it's clear that what happens is going to depend on us, and that this pale blue dot in the cosmos is a special place, maybe a unique place, and also that we are its stewards at a especially crucial time, especially crucial century. And that, I think, is a message for all of us, whether we're interested in astronomy or not. So thank you very much.
Martin, thank you very much indeed. Questions?
There has been one sort of evolutionary cycle which was stopped by something, or possibly stopped by something very large hitting the Earth. Do cosmologists have anything to say about how likely that is to happen again?
Well, we do understand asteroids and what that risk is, and it's fortunately low risk, but it's easier to quantify that risk than many of the others that we can. And so we know that an asteroid like the one which probably finished off the dinosaurs would impact once every 10 to the 8th years or thereabouts, and smaller ones more commonly. And so we do know that we are at risk from asteroids. It's not the kind of risk to keep us awake at night. I mean, I'm more concerned about the human-induced risks, which are much higher now than they were in the past. The risk of an asteroid impact is no higher now than it ever was, and it's something which we can quantify. But of course, as I mentioned, it's a matter for debate. What would have happened if those particular asteroids hadn't landed at the time they did? Would mammals have still taken over or not? And that, of course, is another uncertainty in working out the probability of the kind of evolution that happened here on Earth if you had starting conditions rather like the starting conditions on the Earth. But we can quantify the risk from asteroids, and just obviously the one that killed the dinosaur was about 10 kilometers across. The one that landed in Siberia about a century ago and devastated a forest, about 100 square miles, that was about 100 yards across. And that happens every few hundred years. One hopes the next one will miss highly populated areas. And intermediate asteroid scale, say half a kilometer, they're more serious if they land in the ocean. Because if they land in the middle of, say, the Atlantic Ocean, they produce a tsunami hundreds of meters high, and that would be the main catastrophic effect. But again, these don't keep me awake at night because they have very small risks, but they're quantifiable risks. And just one point, in the long run, we may be able to do something about them, because if one knows the orbits of asteroids well enough, then obviously you can identify many years or even decades in advance those that might come close, and it might be possible in future decades to sort of nudge them into a different orbit.
You mentioned about seeing planets in front of suns.
Yes.
Is there anything you can actually tell what the orbital plane of planets?
Well, of course, they're indetectable by that method if we are looking in the orbital plane. And so when we know how many Kepler has detected, then, of course, assuming that the orientations of the planes are random, we can infer that the total number is going to be higher than the number that we see by some geometrical factor, which you can calculate, and is probably about 50. Because the alignment has to be within about half a degree in order for us to see the occultation.
We don't know which stars to look at.
No. So the Kepler spacecraft is looking at 100,000. Okay, and I mean, supposing that it detects, say, 100 planets like the Earth, then from simple geometry you could say, well, that probably means that around those stars there are maybe 5 or 10,000 altogether. Yes?
I'm interested in your views about dark matter, and I understand there's also dark energy. Do you think they'll turn out to be real phenomena, or are they symbolic of our lack of understanding?
Oh, no. Dark matter, I think, is certainly there. This is particles which contribute about 80 or 90% of the mass of all galaxies, and without which galaxies would fly apart. You couldn't understand their dynamics, and you couldn't understand their formation. And in those, the calculation I showed, two galaxies crashing together, then you get a quite different result if you don't put in the dark matter. So all we can say is that the dark matter is some kinds of particles that are electrically neutral and so don't emit or absorb light. And we can infer their total amount. We don't know what they are. They may be the kind of things the LHC will find. We may detect them directly. But I think there's nothing implausible about their existence. There are lots of candidate particles, and there's no reason why everything in the universe should shine any more than everything on the Earth shines. So I don't think that's mysterious. What's called dark energy is slightly different. This is some feature of empty space, which actually causes the expanding universe to accelerate rather than slow down. Because if there was just the gravity of all the galaxies, you would expect that the expansion would gradually be slowing down. But in fact, that is not observed to be the case. And for the last half of the universe's age, it's been speeding up, not slowing down. And what this tells us is that there is some sort of energy, like a sort of tension in empty space, which pushes things apart and cancels out gravity. And this is sometimes called dark energy. And this is very mysterious indeed. And I think we won't understand that until we've achieved the unification at the top of the snake, which I mentioned, because it's probably an effect of space at the most fundamental level. And most people expect that just as this lectern, if we chop it up into smaller and smaller pieces, we get out atoms, most people suspect the same is true of space. And you can't divide space or indeed time indefinitely. And when you get down to a certain scale, space develops very complicated properties. The problem is that the scale on which the structure of space is expected to manifest itself is a billion times smaller than an atomic nucleus, 10 to the minus 33 centimeters. So that's very far from being observed. But on that tiny scale, then many people, particularly those who are developing so-called string theories, believe that what we think of as a point in space, if you magnify it enough, is actually a sort of tightly wrapped origami in several extra dimensions, which we don't detect because they're not wrapped up. So that's a long way of saying that the nature of space at the tiny level is very complicated, and until we understand that, we won't understand why there is this force which causes an acceleration of the universe. This force is overwhelmed by gravity locally and even in our galaxy, but when everything else is so dilute and therefore gravity is not very effective, then this force dominates. That's a rather long answer to the question. Yes?
One of your earlier slides, you showed you had stellar wind.
Yes.
What is stellar wind?
Well, that's a particles being blown off. Of course, the sun has a wind, the solar wind, which is particles coming out of the sun, which of course interact with the magnetosphere, produce the aurora, etc., and their strength depends on the solar cycle. So that is an example, and most stars have winds, but the kind of winds that were mentioned there were those that carry a much larger mass flux than the solar wind, and would be a way in which the star can lose quite a bit of its material before it eventually ends its life exploding. The solar wind is carrying away 10 to the minus 14 solar masses per year, so that's only 1 part in 10 to the fourth of the sun's mass over its entire lifetime, whereas some stars have winds which are halving their mass over their lifetime, and so the replenishment of interstellar material from stars comes partly by steady mass loss via winds and partly by the explosive mass loss. But most stars have some sort of wind coming out, including the sun.
Well, Martin, all I can say is fantastic. Thank you. What a wonderful start to the series. And I just want to hand over to Rebecca, but firstly, thank you very much.
To thank the Vice-Chancellor for chairing this evening, and of course a huge thank you to Lord Rees for an incredibly stimulating lecture. I think we could hardly have got off to a better start with our Mattingly lecture series. So as a small token of our thanks and our appreciation, I'd like to present you, Martin, with a gift. Just a small token, but thank you very much. It goes goes without saying, of course, that events such as these don't happen by themselves. So I also have a great deal of thanks to give to my colleagues, without whom tonight wouldn't have happened. So thank you to my colleagues. And I'd also like to say that I hope that we'll see many of you back here at the Institute of Continuing Education at Madingley Hall, not only for future Madingley lectures, which are listed in your programme and also on our website, but also studying with us, whether it's for one of our astronomy courses or some other of our courses that have caught your imagination. And I should say that we have a huge range of courses, so there's a lot of scope for catching your imagination. We have typically over 10,000 student enrolments per year, and offer short, non-accredited courses through to accredited undergraduate and postgraduate level programs, through to part-time master's degrees, in subjects for your personal interest and for professional development and diversification, as well as our international summer schools that attract well over 1,000 students to Cambridge each year. So all in all, we're helping to share Cambridge with the world and to enrich and transform lives. So all of you will be very welcome to return to us again. So thank you.